All right, and I think we should probably get started. Can everybody hear me?
Yes, I
I
can
can.
hear you.
All right, great, thanks. Mm-hmm. Let me maybe share my screen. All right, so today I wanted to finally move on to talking about some of the model structures we will need for the actual definition of a Funtorial field theory. Let's recall that last time we did mention transfer model structures. Let's see, where was this? Yes, so we get some model categories, we get the unquilling model structures, we get given interpretation of concomplexes. And we did mention transfer model structures. So a transfer model structure is transferred along a right adjoint functor. You have a model category C, and you have a right adjoint functor R from D to C. And you say, okay, I'm going to create a model structure on D by declaring that weak equivalences and fibrations are induced by the functor capital R. The transfer model structure does not always exist, but of course, when it does exist, it is defined uniquely because weak equivalences and fibrations determine all the other classes of maps. And we gave some examples. The first example I think would be very classical is the category of topological spaces. It has a right adjoint functor, which is the singular complex functor, lands in simplicial sets. And if we equip simplicial sets with the conquilling model structure, then you can transfer this model structure to topological spaces. And that was already how basically the model structure in topological spaces was first constructed by Quillen himself. You can do very similar tricks, and this will be relevant for what we do later by transferring the model structure and simplicial sets along the smooth singular complex functor to smooth sets, which almost immediately tells you that smooth sets are Quillen equivalent to simplicial sets. So both of these functors will induce weak equivalences of the underlying relative categories. So smooth sets are a model for homotopy types. In particular, they're also equivalent to topological spaces. Another very important example is the forgetful functor from simplicial objects in abelian groups. So these are just functors from delta up to abelian groups. And abelian groups make a forgetful functor to sets. And it was first, I think, observed by Quillen that the conquillen model structure in simplicial sets transfers to simplicial abelian groups. And why is this important? Well, something called the Gauge-Kahn correspondence establishes an equivalence of categories between an equivalence of categories between simplicial abelian groups and non-negatively graded chain complexes. And the functor in one direction is familiar to you guys as the normalized chains functor. So you say that the normalized chains of some simplicial abelian group capital A in chain degree n, this will be an as an abelian group. And then you get a quotient by a degenerate simplices, which happen to form a subgroup. It's easy to prove, and therefore this definition makes sense. And the differential is induced by the alternating sum of face maps, which I'm going to denote by di here. So the face map, the i's face map removes the i's vertex from a simplex. So if you have ever seen, say, simplicial or singular homology uses this construction as an intermediate step. The singular homology first takes a topological space and applies the singular complex functor to get a simplicial set. And then it computes the normalized chains using this recipe. And you get a chain complex, the singular chain complex. And this is basically the very typical example, a very typical example for the Gauge-Kahn correspondence. And what is remarkable is that the normalized chain functors happens to be an equivalence of categories, and it has an inverse functor, which is traditionally denoted by gamma, and that's also called a Gauge-Kahn functor. And let me maybe correct its name. It sends a chain complex to a simplicial abelian group. Sometimes this construction is known as a simplicial Eilenberg-MacLane space, because as a special case, if you supply a chain complex concentrated in some degree n, where it is given by some abelian group A, then the functor gamma will produce a simplicial abelian group whose underlying simplicial set has a single non-trivial homotopy group in degree n, where it is exactly A. So these considerations, part C and part D together, induce model structure and chain complexes. This is known as a projective model structure and chain complexes. And maybe a couple more examples that I should probably mention just to give you a flavor or maybe some intuition in what settings you can expect the existence of transfer structures, differential graded algebras, algebraic transfer structures. So here on the right, you have the projective model structures that we just constructed. And on the left, you have respectively monoid objects or commutative monoid objects in the category of chain complexes. And this was also, at least for the commutative case, was originally observed by Quillen and in connection with his work on rational homotopy theory. In fact, much of model category originates in rational homotopy theory, I think. So do many other branches of mathematics, like derived geometry and deformation theory, by the way. That was one of the Fields medals. I think the only Fields medals that was given to an actual abstract homotopy theorist. All right. Any questions about these examples before we move on?
Please, can you repeat about example B?
Example B, you have the category of smooth sets. So that's just functors from card up to sets. And optionally, you can also impose this sheaf condition. And formally speaking, you have to, because smooth sets are defined as sheaves of sets. And given such a functor, you can evaluate it on what is called the extended smooth simplex. Maybe I should say what the extended smooth simplex is. So smooth sets, maybe I should use just black. Smooth sets are sheaves on Cartesian spaces. So let me put sheaf here. And inside Cartesian spaces, you have delta n, or maybe I should use bold delta. This is just points in, how should I say, Rn plus 1, whose sum of coordinates equals 1. So here are some examples. The zero-dimensional simplex is just a point inside R1. The one-dimensional simplex will be a line. The two-dimensional simplex will be a plane embedded in R3, and so on. And the way you think about these guys is that inside of here you have vertices with coordinates 0 and 1. And likewise here you have actually 3 sides. So these sides have coordinates x0 equals 0, x1 equals 0, and x2 equals 0. So it's just like the ordinary simplex, except it is extended in all directions. The reason we want to extend it is because delta n is representable. It's an object in Cartesian spaces. And this allows us to, so it is also in particular a simplicial object because, for example, a phase map will send delta n to delta n plus 1 by setting one of the, inserting a 0 as one of the coordinates. And likewise, a degeneracy map will take the sum of two consecutive coordinates. So now you can evaluate any, say if you have a simplicial set F, you can evaluate F on an n simplex, which gives you a set, and this will be a simplicial set. And this is what is called the smooth singular complex. It has different properties in the usual topological singular complex. For example, the topological singular complex is always a concomplex, whereas here you don't really ever get a concomplex. And the reason for that is that the topological form, topological simplex retracts onto a horn. For example, in the topological situation, you will have a map. So you will have an inclusion map from a two-dimensional horn to a topological true simplex. So this map includes these two sides, and it has a retraction which keeps these two sides unchanged and projects, so to say, everything in the vertical direction. And this map is not smooth, so such a trick will not work in the smooth case, which makes the theory different. But ultimately, what is remarkable is that despite these problems, like I just demonstrated to you, the transferred model structure exists and is a Quillen equivalence. So there is also a left adjoint, which in complete analogy to topological spaces is called the smooth geometric realization. And it is a theorem that this junction is a Quillen equivalence. Yeah, so you are free to use smooth sets as models for homotopy types. And this is not just a curiosity that you sort of look at once and forget, because it's actually used in the geometric cobordism hypothesis, because at one point you basically need to encode, well, very roughly speaking, and this is not quite what is actually in the paper, but to simplify things quite a bit, you may want to encode something like the diffeomorphism group of some smooth manifold M. And it's quite easy to return such a so M is a smooth manifold, or if you want, it will ultimately, of course, be a Bordism. And it's quite easy to return such a group into a smooth set by declaring that S points, which you should think of as smooth maps from S to diffeomorphisms. Well, diffeomorphisms are in particular endomorphisms, and you can say these are just smooth maps from S times M to M, so that for any point in S, the resulting, if you evaluate at this point in the first argument, the resulting map from M to M is a diffeomorphism. So this encodes the diffeomorphism group as a smooth set, in fact, a smooth group, because it also has a group structure. And it's smooth, so it's a little proposition, which of course I'm not going to prove for you here, but the smooth singular complex of the diffeomorphism group is weakly equivalent to the topological singular complex of the diffeomorphism group as a topological group equipped maybe with some kind of Whitney topology. Oops. So the traditional answer, in fact, is homotopy equivalent to our Schiffi answer. All right, any questions? Excellent. Let me now move on to a sort of very important transfer model structure, namely the transfer model structure, or also known as the projective model structure, on functors, or equivalently on diagrams, or equivalently on presheaves. So the setup here is that you have a category C and a model category M, and you consider the category of functors from C to M. And if C is the opposite category of some other category, then what you get is called the category of presheaves on that category. And you want to construct a model structure. And there is a sort of an obvious forgetful functor to from this category to a much easier category, which is given by the product. So this notation just means the product of as many copies of the model category M as there are objects in C. So what this functor does, what this forgetful functor does, it evaluates on objects. So the way you think about this is, as before, you have some algebraic structure on the left, and some easier structure on the right. And here, if you know the value of a presheaf on objects, to specify an actual presheaf, you have to specify the maps associated to morphisms in C. And these maps, you think of them as additional algebraic operations on your collection of objects. And the condition that these maps have to satisfy functoriality is like an algebraic condition, an algebraic identity that these algebraic operations have to satisfy. In fact, if you are familiar with a tiny bit of universal algebra, you can say that the category of pre-sheaves or functors from C to M is it can be specified as algebras over a multi-sorted algebraic theory. You may be familiar with one such theory, modules over a commutative ring. To specify a module over a commutative ring, you have to specify a commutative ring and a module. So two different sets must be specified. The underlying set of a commutative ring and the underlying set of a module. And so this means the category of modules over commutative rings is a true sorted algebraic theory. Here, it's a many sorted algebraic theory where you have as many sorts as objects in C. And a theorem due to Kang, I should say, it says if M is a cofinitely generated model category, and cofinitely generated simply means, and maybe I should have said this, but cofinitely generated means that the acyclic fibrations in your model category are given by maps with a right lifting property with respect to some set of cofibrations. So let me put it like this. I think we introduced this notation with a pitchfork earlier. Let's see. Is it present here on the left? Yes. Yes. So you may recall that this pitchfork notation simply means the morphisms with a right lifting property with respect to a given map. And since you already know that in any model category, acyclic fibrations are precisely those maps that have a right lifting property with respect to cofibrations. Here, the condition is a slight generalization of that. You say, okay, we know that the maps with a right lifting property with a class of O with respect to the class of all cofibrations are precisely acyclic fibrations. And the way this condition is stronger is that capital I is required to be a set as opposed to a proper class. So cofibrations in a typical model category would form a proper class. And if you can find inside this proper class an actual set with a property there that maps with a right lifting property with respect to the set are again acyclic fibrations, then you say that elements of capital I are generating cofibrations. And most model structures that will be of interest to us, pretty much everything will be cofinitely generated. And as an example, let me remind you that the Conquillan model structure, in the Conquillan model structure, fibrations, respectively acyclic fibrations, were defined using a right lifting property with respect to a certain collection of maps, namely inclusions of boundaries of simplices into simplices. And these inclusions are precisely the set of generating cofibrations. which thus shows that the concurrent model structure is cofinitely generated. All right. So this condition is not a very restrictive condition. It can be satisfied in pretty much every single example of interest clause. All right, and so typically you can expect the projective model structure of functors to exist. And in this model structure, a morphism, so morphisms here recall are natural transformations. Morphisms of functors are natural transformations of functors. And such a natural transformation is a fibration or a weak equivalence, even only if its components are fibrations, respectively weak equivalences. And in some cases, cofibrations will typically be more difficult to describe, but in some cases, it is possible to describe cofibrations explicitly. And one of such cases is the projective model structure on simplicial presheaves. So in the projective, so if M is simplicial sets, then with the concurrent model structure, then a natural transformation is a cofibration if and only if the following condition holds. And the condition, first of all, recall that a simplicial set is a simplicial object in simplicial sets. And so what happens here is we are reinterpreting, and maybe I should have said this somewhere. You know what? Let me squeeze. This. And what happens here is we reinterpret functors from C to simplicial sets, which are just simplicial objects in sets. Well, we can reinterpret this as simplicial objects in presheaves of sets. And after we reinterpret in particular, a natural transformation will now be a natural transformation of simplicial objects of this type. And now we can say that a natural transformation of simplicial presheaves is a cofibration if and only if, interpreting it as an object here, for any n, the value at an n simplex, which is in, so this Tn is a presheaf of sets. Tn splits as a coproduct or disjoint union of degenerate n simplices. So the part of the presheaf that is in the image of simplicial degeneracy maps, and some other presheaf of sets, which you can think of fairly reasonably as the presheaf of non-degenerate n simplices. And this condition is non-trivial because, generally speaking, non-degenerate simplices will not form a presheaf because applying a structure map in capital C to a non-degenerate simplex can actually give you a degenerate simplex. And so for a typical presheaf, non-degenerate simplices are not going to split off in this manner. They will be fused into degenerate simplices in some non-trivial way. And the second condition you have to impose for being a, well, I guess I said here I said a cofibration, maybe I should say cofibrant object, because that's what I decided to stick to. Oops. And the second condition you have to impose is that Tn, the non-degenerate simplices, are themselves a coproduct of retracts of representable presheaves. So, for example, if C is cart up, so we are dealing with presheaves on Cartesian spaces, then basically simplicial presheaf on Cartesian spaces will be cofibrant if non-degenerate simplices split off, and the presheaf of non-degenerate simplices looks like a disjoint union of a bunch of Cartesian spaces. And a typical example of that later will be the Czech nerve. The Czech nerve will be projectively cofibrant. Okay, any questions about the Transberg model structure?
Please, can you reveal a bit intuition behind of this notion?
Which one? Sorry. Which notion?
About transfer model structure. Intuition.
I would say the thing to remember here is that you can expect or should look for a transfer model structure if your model category is specified using some. If objects in your model category are specified using some algebraic operations and algebraic identities between them. And I mean, the only other intuition you can keep in mind is that weak equivalences are created by the forgetful functor. Yeah, so in these examples, you can see all these examples, the weak equivalences are always induced on the level of underlying objects. So here, a weak equivalence will be a quasi-isomorphism of the underlying chain complexes, for example. And all these structures are specified using algebraic, sort of, they all have an algebraic flavor. And this is what you can typically expect to happen is that whenever you have such an algebraic setting, you can expect a transfer model structure.
Thank you.
All right, so I think I may have mentioned one more. Let's see. Yeah, we'll revisit this later when we compare transfer model structures to left Gaussian localizations. All right, so let me very briefly mention as a motivation for what we do later, just a very brief mention of a result due to Dwyer and Kahn from 1980s, which sort of connects to what we studied previously, the hammock localization. Let me pull it on the left screen. So previously we studied the hammock localization, which starts with a relative category and extracts so a relative category and produces a simplicial category. And it was given by this somewhat non-trivial construction, which for vertices, you will already see some zigzags of formal compositions of morphisms and their inverses. And there is a non-trivial equivalence relation you have to impose. So this is all pretty non-trivial and not so easy to study directly. And one of the main advantages of model categories is that for a model category, the hammock localization, so you can, if you have a model category C, you can take its underlying relative category, which is C with a class of weak equivalences. You can take its hammock localization, LH of CW, and you can ask about simplicial mapping spaces in the hammock localization. So this is what we really are interested in any relative category. We are interested in computing this space, the mapping space between two objects. And the advantage of model categories, if you have a model category and it satisfies some additional condition of being, say, a simplicial model category, or more generally, you can say an enriched model category will do. And all examples we studied so far are simplicial or enriched over chain complexes. So this is not a particularly restrictive condition. So in a simplicial model category, you have a simplicial set of morphisms between any two objects. And this simplicial set satisfies an additional axiom. And the theorem of Dwyer and Kahn is that if you have a simplicial model category and you have a cofiberic object X and a fiberic object Y, so let's recall this means that the unique map from the initial object to X is a cofibration, and the unique map from Y to the terminal object is a fibration. So if X is cofiberic and Y is fiberic, then the simplicial, the enriched Hom from X to Y, so the simplicial set of maps from X to Y happens to be weakly equivalent to the hammock localization from X to Y. So you see, you have a very, very simple recipe. If your model category is enriched in simplicial sets, for example, then you can compute this very complicated and very difficult construction just by computing the or taking the enriched Hom that is given to you. So for example, in simplicial sets, all simplicial sets are cofibrant, and the fibrant ones are precisely Kahn complexes. So the hammock localization, if X is a simplicial set and Y is a Kahn complex, you can compute the simplicial set up to a weak equivalence as just the internal Hom in simplicial sets. And slightly more generally, if x and y are arbitrary, you can use the axioms of a model category to factor the unique map from the initial object to x as the composition of a cofibration followed by an acyclic fibration, as indicated here. And likewise, the unique map from y to the terminal object can be factored as the composition of an acyclic cofibration and a fibration. Then these intermediate objects are called cofimate replacement and fimate replacement. Their main property is that they are weakly equivalent to x, respectively y, and they are cofimate, respectively fibrant, because this map is a cofibration and this map here is a fibration. And now the second part of the theorem shows that if you want to compute the Hammock localization between two arbitrary objects, the mapping simplicial set in the Hammock localization between two arbitrary objects, then you can simply take the enriched Hom object in your category C from the cofimate replacement to the fimate replacement. And in case you're interested how this map works, given such a map F from Qx to Ry, you send it to a hammock of length 3, where F is placed in the middle, and these canonical maps from Qx to X and from Y to Ry are placed as formal inverses of weak equivalences. And this procedure should remind you of many things in homological algebra, for example, where you compute. So in homological algebra, you work with the category of chain complexes. And for example, the transfer model structure is called the projective model structure in this case. And as it happens, the cofimate replacement functor will be just a projective resolution you are familiar with from homological algebra. And in particular, this means that if you want to say compute the derived, maybe I should have mentioned another notation for the left side or the right side, well, strictly speaking, the left side, I guess, is called R map, and it's referred to as the derived map in space. So derived refers to the fact that you are taking the cofimate replacement here and the fimate replacement here. So the derived map in space is just something weakly equivalent to the map in space in Hammock localization. And in homological algebra, you see many examples of this. Such as, for example, the if you want to compute the X groups, between two abelian groups, or more general, between two chain complexes, then you would be precisely computing the derived map in space in chain complexes. So you would compute the cofimate replacement. So all chain complexes are fibering in this model structure, and cofimate replacement is just projective resolution. So you replace the source, the X, with this projective resolution, and then you will compute the ordinary internal Hom in chain complexes. And then if you take the homology groups of this internal Hom, you will see the X groups. Yes, typically denoted by the upper N. Maybe. Yeah, I think it's typical the upper script. Yeah, so the homological algebra, as you may recall, is full of such recipes where you replace something with a projective resolution. And as it turns out, all these recipes really talk about derived mapping spaces or more generally derived functors. All right, so maybe we can summarize the discussion so far is that, yeah, transfer model structures work well for algebraic structures with strict identities and uniquely defined operations. I'm going to just click here a bunch of examples. All the examples you are familiar with, like chain complexes, differential gradient algebras, commutative differential gradient algebras, but also operatic constructions such as A infinity DGAs, E infinity DGAs, simplicial groups, simplicial monoids, simplicial rings, simplicial commutative rings, uh, structures like A infinity categories, symmetric monoidal categories, simplicial categories, all admit transfer model structures. Algebras over operands, which subsumes part B as a special example and also part A. Yeah, so whenever you have strictly defined algebraic operations, you can expect a transfer model structure. And strictly speaking, for commutative DGAs, you would expect it only for rational commutative DGAs, because for characteristic P, you would need E infinity DGAs. And this really has to do with the fact that not every E infinity DGA in characteristic P is weakly equivalent to a commutative DGA. But let's not worry about this too much. It's not particularly relevant for what we want to do later. Okay, so in what we will study later, we will need also examples of a different type, where instead of some strictly defined algebraic operation, you only have algebraic operations defined up to a contractible choice. We have already seen some examples of this, where, for example, when we talked about Kahn complexes, we saw that in a Kahn complex, yeah, when we talked about interpretation of Kahn complexes, we saw that morphisms are one simplices and triangles, two simplices in co-composition. But for a given pair of morphisms f and g, there's more than one triangle that fills it out, and therefore there is more than one candidate with a composition H. And the way this problem is resolved is you observe that the collection of all H's can be organized itself into a simplicial set, and this simplicial set is contractible. So even though composition is not uniquely defined, it is defined uniquely up to a contractible choice. And we will see many more such examples. For example, in the notion of a, say, complete Siegel space or a Siegel category, you can talk about simplicial monoids or monoids where the operation of multiplication is defined not uniquely as a strict algebraic operation, but only up to a contractible choice. This will be somewhat similar to the problem we saw here. So we'll need many such structures in what follows. And just to give you some examples, maybe one example that we will consider almost immediately will be the example of sheaves and the homotopy coherent descent condition, where the operation of gluing a compatible family is not defined as a strict algebraic operation, but only up to some contractible choice. So let me recall very briefly how sheaves work in the traditional setting of sheaves of sets, and what exactly is going to change when we switch to the homotopy coherent setting. And this will be, I guess, directly relevant for Funtorial field theory because now, of course, we will later see that the model category of smooth symmetric monoidal infinity n categories is in fact a certain left pulse localization of a category of simplicial presheaves. So we are finally moving on to describing the model categories that are actually used in the paper. And one of those actually was already described previously. Of course, the transferred model structure on presheaves will be used as the sort of steps going toward the final model structure. Okay, so let me recall that if you have, say, some psych S, for example, S can be Cartesian spaces, then I can consider the category of presheaves on S, which is defined as contravariant functors from S to sets. And inside this category, I can identify the category of sheaves on S, which is singled out by the gluing condition, which says a presheaf is a sheaf if any compatible family glues to an honest section. So sheaves sit inside presheaves as a full subcategory. And this inclusion functor has a left adjoint. The left adjoint is called the associated sheaf functor. It takes a presheaf and turns it into a sheaf in a universal way by requiring that maps from a presheaf to some other sheaf are the same as maps from the associated sheaf to the same sheaf. And there is one more way to describe the category of sheaves, which will be very, very important for what follows. And this is the category of fractions. So we start with an observation that the associated sheaf functor creates a relative category structure on presheaves. Namely, you declare that a morphism of presheaves is a weak equivalence if after applying the associated sheaf functor, you get an isomorphism here. So this creates the associated sheaf functor creates a notion of a weak equivalence, which is called a local isomorphism. And you can form, so since the associated sheaf functor sends local isomorphisms to isomorphisms, you can form the category of fractions of pre-sheaves with respect to local isomorphisms, meaning you formally invert local isomorphisms. And the associated sheaf functor will factor in a universal fashion through this category of fractions. So since the associated sheaf functor sends elements, sends local isomorphisms to isomorphisms, it will factor like this gashed functor through the category of fractions. And a remarkable property of the category of sheaves is that this functor is an equivalence. This factorization is an equivalence of categories. So in particular, if we compose this equivalence with the inclusion of sheaves into pre-sheaves, like this, we see we get this green functor going in the opposite direction, and the green functor is a Reich adjoint to the localization functor. So the Reich adjoint functor is a fully faithful functor. It's fully faithful because it's a composition of an equivalence of categories and an inclusion of a full subcategory. In such a situation, when the localization functor has a fully faithful Reich adjoint, is known as a reflective localization. So now we would like to replace sets here with simplicial sets. And the question is, to what extent does this picture generalize to simplicial sets, to pre-sheaves of simplicial sets? And it turns out pretty much almost everything generalizes. And instead of here you have a diagram of categories and functors between categories. And here, the analog of this will be a diagram of relative categories and relative functors between categories. And maybe we should start with discussing how pre-sheaves are generalized. So pre-sheaves will now be simplicial pre-sheaves. So this will be pre-sheaves of simplicial sets. Morphisms of pre-sheaves will be natural transformations. And weak equivalences will be natural weak equivalences. So weak equivalences in the transferred model structure. So this relative category is just the underlying relative category of the transferred model structure. Now, inside this relative category of simplicial presheaves, we will single out an analog of the notion of a sheaf, which in the context of model categories is called a local object. And as before, we are going to see an inclusion of relative categories. It will be what is called a fully faithful inclusion, which means not only it includes, so first of all, it's an inclusion of a full subcategory in the usual sense. The notion of a weak equivalence here is induced from weak equivalence here, so it's the same. And finally, it's also an inclusion in a certain homotopy coherent sense. If you take the induced underlying functor on simplicial categories by taking the Hammer localization, then you will see on every simplicial mapping space, you will see a weak equivalence of simplicial sets. So it's also a fully faithful inclusion of the underlying simplicial categories in the homotopy coherent sense. We are also going to write down an analog of the associated sheaf functor. We'll send a simplicial presheaf to the associated local object. Unfortunately, there is no a single universally accepted name for local objects in the context of simplicial presheaves. You can either say infinity sheaf, but this also brings some inappropriate associations with quasi-categories, which we are not using at this point. So, but that's basically the only invocation we have. Yeah, so there's an analog of the associated sheaf functor. As before, it creates a notion of a local weak equivalence of simplicial presheaves. Namely, you would say that the natural transformation is a local weak equivalence if after applying the associated sheaf functor, you get a natural weak equivalence of the associated sheaves. And if you equip simplicial presheaves with this new notion of a local weak equivalence, so you replace the class of weak equivalences with a class of local weak equivalences, you get something like the analog of this category of fractions. Let's recall that in any relative category, you think of weak equivalences as something that you formally invert. So if I enlarge the class of natural weak equivalences to the class of local weak equivalences, I can phrase this by saying this is like a homotopy coherent analog of the category of fractions. And we do have a sort of a construction that will take this further by taking the hammock localization of this relative category. You will see the what you can call the simplicial category of fractions. Okay, so now we can compose so since the associated sheaf functor sends local weak equivalences to natural weak equivalences, it induces this functor here right away. So this functor will be a relative functor. It's a functor that preserves weak equivalences essentially by definition. Maybe I should pull the diagram on the left. So this functor is the analog of this gashed functor here. And of course, there's we expect it to be a weak equivalence of relative categories. And in fact, there is a fairly obvious functor going in the opposite direction. You can include local objects into all objects. Morphisms are the same. And every natural weak equivalence is, in particular, a local weak equivalence. So this is the analog of the, well, I guess Dmitri would even say what this functor is here, but you can compose the inclusion with the localization functor and you get a functor in the opposite direction. Maybe I should have, anyway. And finally, now we can also see that the role here, the role of the localization functor here, is now played precisely by the identity functor. Well, it's not strictly speaking the identity because oops, because an identity functor is required to have the same domain and codomain. Here, the domain has natural weak equivalences and the codomain has local weak equivalences. So, but it is an identity functor on the underlying categories. So you think every simplicial presheaf to itself, and you think every natural transformation to itself, and the class of weak equivalences gets enlarged to local weak equivalences. And we do see now that we also have a sort of a right adjoint functor in the homotopy coherent sense. This right adjoint functor will be the composition of the associated sheaf functor and the inclusion. So again, this is basically just the associated sheaf. And I guess it may be slightly confusing that I now say the associated sheaf functor is a right adjoint, when in fact previously it was a left adjoint. In fact, that's what it is here. But maybe I should be more careful. I mean, we saw that this is an equivalence of categories, and here we have an inclusion of categories. So the associated sheaf functor is really what you apply here, and then you take this composition. So it's this functor is induced by the associated sheaf functor, but really it's just modeling the inclusion of sheaves into pre-sheaves. So what we'll see in a second is that here we have the transferred model structure, and here on this lower right corner we have the left bows with the localized model structure. the left ballistic localization of the transfer model structure. And you can already see what this means. What this means is that the underlying category is the same, and the class of weak equivalences got enlarged to a bigger class. And the only other thing we'll have to say is what happens to cofibrations. As it turns out, nothing happens to cofibrations. Cofibrations stay exactly the same. And the upper right corner, this corner, will not be, so this is not a model category. This is just a relative category. It's a subcategory of the model category of simply the transfer model structure, or if you prefer the localized model structure, includes into both. But itself, it's not a model category because, for example, local objects typically do not admit finite limits or finite core limits in the categorical sense. So it's this absence of limits or core limits that prevents us from calling this a model category. Okay, any questions about this example before we move on to the formal definitions?
Please, can you review a bit more about intuition behind of reflective localization and how it is used in field theories?
Well, the applications to field theories will be reviewed later, but for now, let me just say that in general, maybe I should have given you an abstract definition of a reflective localization somewhere here. So in general, reflective localizations encode the following very simple situation. You have an inclusion. Let me just use blank. An inclusion of subcategories. So you have a full subcategory. And if this inclusion has a left adjoint, then such a situation is called a reflective localization. So reflective localization is simply a full subcategory such that the inclusion functor has a left adjoint. So the only inclusion here is that in a reflective localization, you have some category C, some full subcategory, which is called local objects. And the inclusion functor of local objects into the entire category is a right adjoint functor, so it admits a left adjoint functor, which means that giving any object in C, you have its reflection of X onto or into L, which is let me call it, it will be a map from X to X prime, where X prime is a local object, And it has a universal property that for any map from X to some other local object Y, there is a unique morphism that makes this triangle commute. And here, a typical example would be the associated sheaf of a pre-sheaf, right? If you recall, you have a F, a pre-sheaf. What kind of universal property can you expect from its associated sheaf? Well, you can expect a map from a pre-sheaf to the associated sheaf. And it has a universal property like for any other sheaf G, so G is a sheaf. If you have a map, a natural transformation from F to G, then this natural transformation factors through the sheafification map in a unique way. And the reasoning here is very simple. In the associated sheaf, any section of the associated sheaf is given by gluing a compatible family in F, or more precisely, a compatible hyperfamily, but it's not. Since G is a sheaf, once you map this compatible family in F into G, it definitely has a unique gluing. And this is exactly how this gashed map is defined. It takes a compatible family in F and sends it to its gluing, so applies this functor from F to G, and then glues in G to an actual section.
I understand. Thank you.
Yeah.
And how, second question, how this definition is linked to Ballfield localization?
Yeah, so in the Bowles localization, we will do exactly the same thing, but now in a homotopy coherent fashion. So in fact, here are the precise analogs of what we just talked about, and maybe I should have very briefly mentioned that if you have a reflective localization, so here is your inclusion of local objects, here is the left adjoint. The left adjoint creates a class of weak equivalences on C, which allows you to write down a localization functor to the category of fractions. Right, so W is a pre-image, so let me call this, I don't know, L. W is the pre-image under L of isomorphisms in capital L. And the functor L factors through the category of fractions. And this dashed arrow is going to be an equivalence of categories. So what we are going to do now will be a precise analog of this picture where we are going to start with a class of maps that generates W in some sense. So perhaps I should have also mentioned this. So a typical way to construct reflective localizations is to pick a class of morphisms S So S will be a class of morphisms in C. And then you can ask for a universal way to invert morphisms in S so that you get a reflective localization. And as it turns out, there is such a way to do this in a universal fashion. And the result can be presented as a category of fractions of C with respect to the co-saturation of S. So here S hat is the saturation of S. Why is this saturation necessary? If somebody just gives you a set of morphisms in a category, and you just take its category of fractions without saturation, you get some other category which typically will not be a reflective localization. And the reason for that is very simple, is because L is a left adjoint functor. Any left adjoint functor preserves colimits, which means that the class of morphisms inverted by L, so this class here, is going to be a fairly restrictive class. Is going to be closed, for example, under colimits in the category of morphisms, because isomorphisms are so isomorphisms in L are closed under colimits in the category of morphisms in L, and left adjoint functors preserve colimits. So therefore, the preimage of isomorphisms is also going to be closed under colimits in L. Colimits in the category of morphisms in C. So that's already one restriction. The other restriction is that L preserves co-base changes, and co-base changes of isomorphisms are again isomorphisms. So the class W is going to be closed under co-base changes. So in fact, that's exactly what the saturation does. This is just closure under co-base changes and colimits in the category of morphisms in C. Oops, sorry. So starting with any set of morphisms S, you can saturate S under these two operations, and you get a bigger class, which need not be a set anymore, even, and you can take the category of fractions, and this will be a reflective localization. And it will be this construction that we will be trying to generalize. And by the way, to get sheaves in this manner, you can take for S, so in the case of sheaves, maybe I should say sheaves S will be Czech nerves of open covers. So if U is a cover of X, then if you may recall, a few lectures ago, we talked about Czech nerves and how they detect compatible families to U, and that's what we will end up using. It will be this picture that we will be generalizing through the setting of model categories. So let me now actually give you the definition, and we can continue next time with further details. Okay, so the basic setup will be a model category C, which you think of as a homotopy coherent analog of this C here. And you will have S, a set of morphisms in C, which will be precisely the analog of this S. It's a class of morphisms that you want to invert, and not just to invert, but you also want the localization functor to have a fully faithful right adjoint. So you want the localization functor to be a left adjoint functor, and you want its adjoint to be a fully faithful functor, which will be precisely the analog of this situation here with reflective localizations. So first, our definitions are going to proceed in two steps. First, we will define this analog, the analog of capital L. So I say an S local object is an object in C, such that for any morphism in S, say S goes from A to B, the induced map of derived mapping spaces, which we defined previously, or if you want, you can also use the Hammock localization here. That's also fine. Let me just put the Hammock localization just for fun. So C, W, why was this just R? I'm not sure. The induced map is a weak equivalence. And what this corresponds to on the left side is that in the case of this localization like a set of morphisms, you are, so the adjoint functor will be a fully faithful functor, and its image consists of objects in C with a property that so the image of this inclusion in C is single log by the property that for any morphism S from A to B, so let me say X belongs to L, if for any morphism S from A to B, the induced morphism of sets from B to X to A to X is a bijection. So local objects in capital L, or the image of this inclusion if you prefer, are precisely those objects in C that see, so to say, see morphisms in S as isomorphisms, in a sense that mapping the domain and codomain such a morphism into X produces an isomorphism. So here, what we did is we wrote a precise analog of this for relative categories. So the set of maps in a relative category is replaced with a simplicial set of maps computed using the Hammock localization.
Sorry, maybe a quick question.
So
the Hammock localization of a model category, will it be a simplicial model category?
Typically, I would bet not, because you typically don't expect the Hammock localization as a simplicial category to have. Well, that's actually an interesting question, but to be honest, I don't know a precise answer right away. But I would bet that it's not a complete or co-complete category. because there is no reason why finite limits or colimits should exist in the strict sense.
I see,
So of course,
but you think
they will exist in a homotopy coherent sense, but for a model category, you want actual strict limits and colimits.
okay, thank you.
Yeah. So the homolocalization is if you want a complete and co-complete infinity one category in a weak sense. Yeah. Okay, and then in the next step, we define S-local morphisms. And S-local morphisms will be a precise analog of this S hat. And this is the second property we use. So the second property we use, and I ran out of space here. Let me insert a page. Okay, so it means now I can scroll here. I have a page here, and I so let me copy it here. So my setup is in the usual one categorical setting, I have a category C. I have S, a set of morphisms in C. And then in the first step, I form the class of S local objects. Let's call it L. Is a set of objects in C such that for any morphism S, in capital S, the induced map from C Bx to C Ax is an isomorphism. So that's my L. In this step 2, I form the class of S local morphisms. Let me call it S hat. Is a set of morphisms F from X to Y, morphisms in C, such that for any S local object A, the induced map from the set of maps from X to A to maps from Y to A is an isomorphism. And now, with these two definitions, we can state, well, okay, strictly speaking, I should say maybe some mild restriction like a locally presentable category. If you don't know what this means, just think of a category that has all co-limits. So the existence requires some condition. Then, with these two definitions in mind, here's a theorem. You have a reflective localization where C, L, so the inclusion functor has a left adjoint. And what's more, the category of fractions with respect to S hat is part A and part B S hat equals so let's call the left adjoint, I guess, little l, as hat equals the maps inverted by little l under little l, yeah. And therefore L factors through the category of fractions. And the second claim is that this factorization is an equivalence of categories. So starting from a category and a set of morphisms in this category, we found a way to invert morphisms in S in such a way that the resulting localization, the resulting category of fractions, is a full subcategory of our original category. So the localization functor has a fully faithful right adjoint. So the construction happening here is a precise replication of this in the setting of model categories. In fact, these two definitions make perfect sense, not just for model categories, but also for relative categories. So in a sense, this definition is even more general. It works for relative categories. There's nothing really about model structures here yet. And just to sort of keep you on track, for the case of simplicial presheaves, you will take S to be the set of all Čech nerves of all possible covering families. Then S local objects will be simplicial presheaves that satisfy a homotopy coherent version of the descent condition or the gluing property. And the S local weak equivalences will be precisely the local weak equivalences in the sense of sheaves, which, depending on your site, can be described as stockwise weak equivalences or something similar. Okay, and of course, there is a complete analog of this theorem, which I probably should have mentioned. Let me, in fact, very briefly mention this. So there is a complete analog of this. So and again, you need a model condition. So let's say C is a model category, but with a model condition like combinatorial. So combinatorial means the underlying category is locally presentable, which is not really a severe restriction. And the model structure is confinements generated, which is a condition you have seen before half an hour ago. Then there is a completely analogous diagram of functors. So we previously defined the set of S local objects. Let me denote it by capital L. And we also define this as a class of S local morphisms. Let me denote it by S hat. And once again, you have similar restrictions. So let me take part B first, because that's actually should be logically first. S hat is precisely, well, no, sorry, that's not the case. So first, I should say, we have inclusion of relative categories from L into C. This inclusion has an adjoint, and here it's important to emphasize this will be an adjoint not in the sense of one categories, but in the sense of relative categories or infinity categories. So This just to be clear, this is not an adjunction on the level of underlying categories. So that's why I put this subscript infinity to remind you of the fact that it only becomes an adjunction in the homotopy coherent sense. So this functor L is called the localization functor. And part B now will state that S hat is precisely the pre-image under L of weak equivalences in capital L. So W with a subscript L is precisely the collection of all weak equivalences in the relative category W. And then, as before, we can form the appropriate category of fractions, which in this case amounts to enlarging the class of weak equivalences from the given weak equivalences in C to S hat. So using my notation for relative categories as the underlying category, comma, weak equivalences, I can simply write it this way. So this is the relative category with the same underlying category as C and weak equivalences in S hat. Here, the weak equivalent, so maybe I should write this a bit more. Precisely like C with some weak equivalences W, and you have a canonical functor, a relative functor, which on the underlying category C is just identity. And since the functor from C to L sends elements of W to elements of S hat, sorry, to weak equivalences, the same functor L descends to a functor here, which we can also basically call L. And the second part of the theorem tells you that this functor L is a weak equivalence of relative categories. So after passing through hammock localizations, the resulting functor between simplicial categories will be a weak equivalence in the obvious sense. It will be a homotopy essential surjective functor that induces weak equivalences on objects of morphisms. Okay, and I think that's a perfectly good time to stop and see if you guys have any questions left. All right, if not, then I guess that's it for today. And I will see you next Sunday.
Thank you for your lecture.
You're welcome.
Thanks for the lecture. Bye-bye.
Bye.